In this video, what we'd like to talk about then is the magnetic field or the B field due to a wire. Now, a piece of wire in and of itself doesn't cause a magnetic field, but of course if you run a current through the wire, then a magnetic field can appear in the space around the wire. You may have seen some demonstrations, some pictures of compass needles deflecting and so on and so forth when a current's run through a wire. So the idea of a current then really stabs at the idea that we've sort of tried to get across in previous videos here, that moving charges cause B field to happen. And we were guided by the Biot-Savart Law here, mu naught over 4 pi V cross R hat over R. And I guess I should make sure I get my Q in there. This is the Biot-Savart Law. And so I can see that as long as I have a charge and some velocity, I will get a magnetic field. And there are some geometry things that can be zero and so on, but we've covered those in a previous video. So a moving charge causes a B. Now it seems like then the ultimate in moving charge then is a current. So where a single moving charge, we've looked at examples that are definitely something like a proton or something maybe moving this way with a speed v, and we looked at the magnetic field at certain points around a charge like that. Well, a current seems like it's the ultimate moving charges, because what that is a piece of wire like this with a whole bunch of charges in there, maybe even electrons, or say maybe all being forced to move this way by an electric field which is inside the wire right there. So it seems like to me, if you're in the space around this wire, you can see a whole bunch of charges moving by, and that gives rise to a magnetic field. So that's what we'd like to look at in this video here. What is the B field due to a wire like this? That's what we'd like to look at. All right, a bunch of charges moving a wire, not just one. Before we get started, though, we will have to do a little bit of morphing on the Biot-Savart Law here. In particular, the speed here, or the velocity, let's just think of it as delta L over a delta T. So if I have some charge like this, like a proton, and maybe it moves some little distance delta L, its speed, of course, will be how quickly did it cover that distance, how much time did it take to cover that distance, that's speed, that's a basic mechanics thing. But in either case, I'll go ahead and take this V and plug it into the Biot-Savart Law. Here's the Q, and now I have a delta L over delta T crossed into R hat all over R squared, something like that. So now what I'll do is I'm just going to take this delta T, instead of keeping it under the delta L, I'm going to put it under the Q. And this is still as a vector here. So mu naught over 4 pi, this will be a Q over a delta T, and this will be a delta L cross R hat all over R squared, something like that. So now what I have is, well, let's take a look at something here. If I look at this quantity here, Q over delta T, well, unit-wise, this is coulombs per second. That sounds like a current to me. So see, we've been able to transform the Biot-Savart Law to get away from an individual moving charge now to something that involves a whole current. So let's go ahead and rewrite this. Mu naught I over 4 pi, and this will be a delta L crossed into R hat over R squared. If I put a big box around this here, this is an adaptation or another version of the Biot-Savart Law now that addresses not individual charges moving, but entire currents that could be moving. Mu naught I over 4 pi, not mu naught Q over 4 pi. And of course, the V cross R hat is now a delta L cross R hat. And let's see how that works for a wire. So I'll erase this. And if I erased it too quickly for you, you can hit pause or rewind and check it out. I'll try and get it rewritten up here. So I have B vector is mu naught I over 4 pi, and it's going to be delta L cross into R hat all over R squared, something like that. So there's my Biot-Savart Law. Let's adapt it to a wire now. What's the magnetic field in the region around a wire? So what we'll do is we're going to look at an infinite wire, one that's very long, and we'll just say the wire sort of looks like this. Here's that long wire, narrow and round like that, loaded with charges that are zipping around. And the question I'd like to ask then is, what is the magnetic field right here at this point? Well, this point here is a distance h, say above the wire. So my height h above the wire, I'd like to know what the magnetic field is. The h could be anywhere. Here. It's an infinite wire, but we'll just stick to this one in this case here. Could be anywhere, but we're distance h on an infinite wire. And there's a current I traveling in the wire, so the current maybe is something like these little electrons moving this way. There is a current in the wire like that. So here's the way that we'll proceed. We've got to look at the Biot-Savart Law to do this now. And what we know before, there's some previous videos say on what R hat means. R hat is something about the vector that connects the observation point with the charge. That's all we knew about it from the previous Biot-Savart discussion, where we looked at the magnetic field due to single isolated charge. It still has the same meaning, but what is the isolated charge now? Where is the charge when we're talking about a whole bunch of charges moving the wire? Well, that forces us to look at what delta L is. Remember delta L, the way we looked at it just a second ago, is we thought, well, maybe if a charge sort of moves a distance delta L like that, we put the delta L over delta T and substitute out the V. Just look at the last couple minutes of the video, you'll see what I mean by that. But delta L was some space through which the charge flowed. Now in this case here, the space that the charge flows through is restricted to be inside this wire here. But delta L is not the length of the whole wire. Delta L is just going to be a little segment of the wire like this. There's the delta L like that, just a little segment of the wire that this charge ultimately passes through. All this charge here will eventually go through the delta L. And what we'd be interested in now is if we have a delta L isolated like that, now we can draw an R hat between the delta L and the observation point, and we even have our R hat going in there. But before we start drawing things and getting too excited about where R hat is, let's just ground ourselves and get a nice coordinate system going, say like this and like this. Here's an XY coordinate system which often really helps to get these problems organized here. So like that. There's my observation point like that. Here's my delta L like that. And so now I'm in a position to go ahead and draw that R hat vector. Remember, R hat connects the observation point and the little space through which the charge flows. So there's the R hat like that. So see, I'm already making a lot of progress here. I have a little unit defined that the charge is going to flow through. I have an R hat vector going in there, and I have some things that I can start working with. But another issue, how big is delta L? Is it half the wire, a small percentage of the wire? What? Well, it's going to be even smaller than you think. In fact, instead of delta L, we should call it DL. Because what we're actually going to do to make this problem work out, I'll work over on this side of the wire because it won't affect, I'm going to draw it over here. We're going to slice the wire up into very small slices. There's a slice, here's a slice, here's a slice, here's a slice, and even in between these two slices, there's another slice and another slice there, and even between these two, there's another slice. You can see the problem gets quite messy, at least the drawing gets quite messy, but all of this right here is what we mean of the transition as we go from delta L to DL. So we're going to discretize the problem into very small chunks. These are going to be very small, let's say small paths carrying the current, very small ones. You'll have to agree with me that if you slice up the wire, the current travels through all of those slices. And what is a wire? The sum or the collection of all those slices put together, which is what an integral can deliver to us by the time we're done with the problem. So take the Biot-Savart law, instead of writing it like this, we'll write it as dB is mu naught I over 4 pi, and this will be a dl crossed into r hat over r squared. None of the other stuff changes in there. So this is the differential form of the Biot-Savart law. Its meaning is as follows here. If you have some current that passes through a very small segment of space, a very small dl, this is the very small magnetic field that that current passing through that small segment will produce. That's what the meaning of it is. So now what we should probably do is look at how the DL and the R hat sort of interface with each other, because we have the R hat clearly labeled, we have the L here, and in terms of direction, the DL is sort of pointing this way because we're going, the current's traveling that way through the wire. So we sort of have a delta L down there and an R hat up here. And remember then that the way the cross product works, if we wanted to get a grip on this a bit here, we can sort of write this as DL sine theta over R squared. And you're saying, oh, wait a minute, I forgot to write the R hat. No, I didn't, because remember, the magnitude of R hat is 1. When we expanded DL cross R hat into a DLR sine theta type of thing, like A cross B is AB sine theta, remember the magnitude of R hat is just 1. So there's an implied 1 in here, but that's what it becomes. And now the sine theta here, that still is the angle between R hat and DL. So the theta here is still the angle between them. And it's very clear to see on the drawing here where that theta is. In fact, it's just this angle right in here. There's theta right in there. So we know what that angle is in there. And we also know that the DL here is at any given time, any given hypothetical time, a distance x from the coordinate system right there. So if we look carefully at the triangle, we can sort of work out what that sine is going to be equal to. What is that angle between the DL and the R hat? Well, the way this is drawn here is, it's not really related to my triangle in here, but I do know that this is theta here, this is a straight line. So this angle in here, this is going to get messy, is 180 minus theta. That's what that angle would be in there. So I don't have the sine of the angle, but I can take the sine of 180 minus angle in this right triangle right here. So I can take the sine 180 minus theta, which is just this angle in here, and the definition of the sine is still the same as opposite over hypotenuse. It's going to be h over r, because r is still going to be my distance from the little segment that the current is passing through and the observation point. So the distance is r, the direction is r hat. Looks like everything's coming together. Trig identity will tell you that the sine of 180 minus an angle is actually just the sine of the angle, so all this is actually equal to the sine of that angle that I was interested in. Let me go ahead and put that into my dB equation here. Pi, and I'll have now a dl times h, and the r here will combine with that r squared there to give an r cubed here. So I have sort of a nice form going here. A little bit of confusion though at this point, because what I'd really like to know then is, all right, well, the little dl in here that all the current eventually passes through does generate a little dB at this point, but what is the direction of that dB? Am I worrying about vectors? Do I need to worry about vector components now? I sort of have this dB here. It looks like it's just sort of a magnitude, because I went to this magnitude form of the cross product, but I still need to be concerned with a vector, because maybe I need to break the magnetic field up into vector components now. Let's take a look. What is the direction of this dB? Well, I go back up to the top now. What I can sort of see is that I need to use the right-hand rule to figure out what that direction would be. So I'll do it two ways. I'll do it with my hand. I'll do it with my wooden model. Looks like the direction of the dB is dl cross r. So if I put my fingertips in the direction of dl, which is this way, and curl my fingers into the direction of the r vector like that, the magnetic field points straight up like that. So right here at this observation point, there's going to be a magnetic field pointing straight up at me like that. Let me verify that one more way, just in case you're sort of warming up with the cross product. I'll use my wooden model here. Remember, it's dl cross r hat. So if I put my a vector in the direction of the dl this way, and sort of think of this b vector is sort of moving in the direction of the r hat. Now remember, I can't orient them the way they exactly appear because these are fixed at 90 degrees, but at least in the plane like that, dl is this way and b is out that way. And it looks like no matter how I do that, this third stick points straight up like that, indicating that b is straight up out of the page like that. So it is true that b is straight up. So it looks like I got lucky in this problem here, because the b, in this case here, is all like a BZ. It's all in the Z direction. It's pointing up at me the whole time. So no matter where one of these DLs is on the page here, I'll see the same thing happen. The DB will be straight up at me. So I do not need to worry about any vector components. I'm free to use this expression here as is. So we're pretty close to finishing this up and getting our answer to pop out here. But we do need to finish it right here. So I'll erase this. Let me just copy it up here at the top. Over 4 pi, and it's going to be dl, let me just get rid of this, dl h over r cubed, something like that. Okay. So what do we do now? Well, we're free of the vector stuff because all the b's are in the z direction, so we don't have to worry about vectors since they're all in the same direction. We can just add them. And what I'd like to do now is just sort of recognize that all these little slivers here need to be added up the way we sort of discussed over here. The wire is a collection of all these little DLs. So the last step for us then is we're just going to integrate all the dBs together here. So the magnetic field that I seek is going to be mu naught I over 4 pi. I'll pull all that out because it's a constant, and I'll even pull the h out because this h doesn't depend on anything. And now I'm sort of left with this thing here, this dl over r cubed. So what am I integrating? Am I integrating L or what? Well, be a bit careful now, because I guess we should probably dispense with L altogether, because if you look very carefully, maybe you've noticed this by now, all this L business here is actually along the x-axis. So, of course, the dl here should become a dx. And then the r cubed here, well, r here is, again, that distance from the little sliver of current to the observation point, which can be found from the Pythagorean theorem, which is just going to be h squared plus x squared. So see, r depends on x and dl is x, and so now I see what I see forming is sort of a better integrand here over 4 pi times the integral, and I'll have a dx on the top and a square root of h squared plus x squared all cubed on the bottom. That's what my integral is looking like. So we're running out of room once again. Get this step copy in the top. What I'll also do is I'll rewrite the bottom as something to the 3/2 power. So B is going to be mu naught I h over 4 pi times the integral of dx over h squared plus x squared, all that to the 3/2 power. And there we go. All just set up. So there's really not much else I can do now other than just do the integral, and we're talking about the infinite wire. It extends from minus infinity to infinity, something like that. And I will just say one note here, maybe the problem you're working on is not an infinite wire, maybe you did the finite wire that goes from minus L over 2 to L, something like that. If that's the case, then be sure that you know that this point here would have to be the perpendicular bisector to the wire. Make sure you're midway in between it, and you just change your limits from minus L over 2 to L over 2 and work the integral that way. But if we stick with this one here, you can look up this integral, do it on Wolfram Alpha, or it's in the back cover of the physics book, or maybe you just know what it is. But if I do all this stuff and get it all simplified out, the answer I get is quite nice. It's going to be mu naught I over 2 pi h. And I'm going to put a box around it. So in other words, the answer to this integral here was just something like 2 over h squared. Very simple like that. It's kind of fun when really complicated integrals come out to be so simple like that. But when you take limits as things go to infinity, often some things can simplify. So we have a big result here. It's in the z direction. This is the B field. Outside of a wire with current I in it. So if you have a wire that has a current I in it outside of a wire with a current I in it, let's just say H away. That's how far you are away from the wire. We've got a nice result here. This is the magnetic field that a current in a wire produces. So very clear result that yes, moving charges, or in this case a current, gives rise to a B field. There's the I, there's the B. No I, no B. That's really the generator of the magnetic field in here. And of course the magnetic field decreases in strength as you get away from the wire. And the mu naught and the 2 pi are just constants. Let's just wrap this video up here by just talking about the result a bit and give a little bit of insights here. Mu naught I over 2 pi h. There we go. And here's the wire here. And there's our observation point like that. And it's an infinite wire. It goes infinitely long in all directions like that. So, a couple of things that it means here. One thing is we hypothesized or sort of got from the Biot-Savart Law that the magnetic field was up towards us right there. Points at us the way we work the problem. If you work the problem differently, the magnetic field would actually be going into the page down here, same magnitude. So what that sort of tells you then is if you have a magnetic field that's coming towards you in the top, going away from you in the bottom, then guess what it would be doing is right in front of you. It'd be going down like this. If it was back into the page, it'd be going up. And the magnetic field sort of makes a big circle around the wire like that. So let me redraw this. If the current was coming at us, if this was a current like this, then the magnetic field would be circulating. It doesn't actually circulate like this, but it'd be like here and here and here and here and here. That's what the magnetic field vectors would be doing. And if you so desired, then the way you normally draw these things, of course, you can fill in all the arrows in between there, and you just get a big circle like this that represented the magnetic field around this wire like that. That's what the magnetic field would be doing. The direction can be found from the right-hand rule. Take your thumb, put it in the direction of the current of the wire, wrap your fingers around this way, and that'll be the magnitude of, the direction of the B. If the wire was going into the page like this, of course the magnetic field would be circulating around it like that. Thumb the direction of the wire circulating around like that, B would have that sort of direction. And in either case here, all of these circles here are a distance h from the wire. They make nice circles like that. And of course the magnetic field magnitude that you get is as written, mu naught I over 2 pi h. The magnetic field outside of the infinite wire. And so that's the result for us. It was a nice application of the Biot-Savart Law, and you see that Biot-Savart is a rather complicated law. You're having to process the R hat and the DL and the cross product, do an integral in there and so on, but now we have a nice result we can use. And what's important to carry away from this particular video here, the B field due to a wire as advertised, is you have a magnitude now, and whenever you have a wire, you can also visualize the direction using the right-hand rule. Those are some very important things, because aside from all that complication of finding this result, these two more simple results can be used in lots and lots of problems now, as we'll see. So there you go. B field due to an infinite wire using the Biot-Savart law.